expecting after last lecture to go back to my office and have all these emails to someone explaining how VDD or how come we needed a 4-terminal MOSFET and all that stuff, and there weren't any, and so I had to figure it out, and I wanted to discuss that right now and do some sims from last time. So let's go ahead and open up our course file. And if you recall, last time we said that you had to use the 4-terminal MOSFET if you see this, but the NMOS we didn't. And the reason is because if you have a symbol for ground and a symbol for VDD, you can use the 3-terminal MOSFET and it will automatically connect the VDD to ground, or the body of the PMOS to VDD and the body of the NMOS to ground. But you have to have the symbols in there. So let's go ahead and do a quick sim. I'm going to modify this, and I'm going to do a duplicate cell and call this, whoops, so what cell is this? This is inverter delay. This one, let's duplicate this cell and call it inverter. What should we call it from last time? What did we spend last time doing? Switching point, yeah. So let's call it VSP. And then come in here and modify the VGS here, or the control statement, and do, and let's call this, let's just set my operating point .op. I'm going to make a mistake. VN 0 to 5 and 1 millivolt steps. Oh, sorry, .dc. That wasn't a mistake. That was an unintentional mistake. Okay, so let's go. Yeah, that's the problem, right? You want this to be the name of this, not the node name. Okay, so let's go ahead, since you caught that, and say, let's actually change it so that they're the same, because that's nicer. Say OK. Press S. Put it on the desktop. Come over and run, and let's plot V in. And what should I see when I plot V in? Straight line. V out equals V in, so let's do that. What's that? No, but you know, the thing is, if you always go to the output and the exciting stuff, then you kind of forget the mundane. So then there's V out and there's our inverter. If we wanted to determine the switching point, what would we do? Plot both. And then how do I attach a cursor to V out? Right click there, attach cursor. Let's just put the first one. OK. Move it up. Oh yeah, switching point. Yeah, right around there. Zoom in. It's hard on this low resolution screen to see what's going on. About 2.4, because we size the NMOS half the size of the PMOS. Let's go back. Any questions? Let's do one other exciting thing here, which is to plot the current. I press Control. Where's the current going to show up? The axis. Yep. So there's the current, and it defines positive current flow is from plus to minus, and we're supplying current from the plus terminal out, so away from the plus terminal, and so that's how we get the negative 360. But you can see right here, this is a near minimum size inverter, and we get a considerable amount of current flowing. So we want to be down here below 0.8 volts and above 4.2, below the thresholds. Alright, so let's go back. Any questions on that one? Everybody keeps moving around. Okay. And now I'm going to go, let's go ahead and delete this. Let's delete these.
So
Press.
There is no way to involve.
Right, there's no way to use VDD without a 3-terminal device without putting the power pin in the schematic. So when I want that documented in those videos, so we put this down and down here. press C or change, or what's the other way of doing it? With the menu, edit, change. You know, I do that because I get so used to the key bind keys that forget the menus. Whoops. Edit, change, transistor, apply. Looking good. Now I've got a question. Do I still need this VDD in here? Yeah, I still need the VDD. Now, note I don't need a ground because 0 is universally ground. So now press S, regenerate my netlist. Automatically means it's connected to ground. So if you went into your layout and you were just arbitrarily connecting things to 0, 0, 0, you could do some bad things because you think it wasn't connected. Okay, so get the same exact stuff. Let's go back now and modify it. Why wouldn't I want to use these connectors everywhere? Because then when I do NCC, I get the implied error, and I may not want that implied error. Okay, and what was? Well, we'll come back to that in a moment. So if I go back here and I say, oh, I'll just pull this up. I'm over here, name this VDD, and then generate a netlist. No, I want to make a mistake. And I come in and it says, hey, can't find model L. So it's thinking that L is the 4th terminal of the MOSFET. So I can fix that in the netlist by doing what? Because I may not want to go regenerate. Let's find out. No. Alright, run. V out. There we go. Notice how this is the point of learning SPICE, so you can write things. So you don't have to go back and do the schematic and all. I can just go into the netlist, put it in, and run it. It's quite interesting. Went to the seminar on all LT SPICE and how they do things and the speed. This LT SPICE is surprisingly fast, and if you compare it to other SPICE simulators, it beats other SPICE simulators. Yeah. The thing is, if you go and you look at, there's other ones called Fast Sim, Nano Sim, H Sim. They're SPICE simulators, but they're not true SPICE. They use what's called a table lookup thing. And the fastest calculation is one you don't have to do, where you just go look up the answer. And so those will go through HSim or FindSim, or those they'll take and look and parse. They do with the SPICE simulator, they'll parse the netlist and determine the size of all the MOSFETs. Then they'll generate tables with IV curves of the MOSFETs at finite resolutions. Then they'll generate charge versus voltage characteristics of the MOSFETs, and then they have those two tables. And then when they go past the netlist to HSim or NanoSim or whatever, they just simply go to the table and look the values up, and that's how you're able to do million transistor sims. You can't do a million transistor sim with a SPICE simulator. Okay, someone say, well, it is SPICE, HSim is SPICE. Well, it is, but not exactly, all right, because it's two parts. All right, so, and we can go back and fix this. Let's do a Control-Z a few times. Let me see. Oh, the other thing. No, when I was doing I don't know what I was doing, but I was doing an LVS. Let's look at this one. There's my inverter. There's the. Now, will this thing, if I put it in a simulation and make an icon, will this thing simulate without problems? No. Because if I do an NCC, though, press L, no errors, right? If I go, I'm going to show you something you need to be aware of because you want to get good grades on your project. So, I'm going to get rid of these. Let's go ahead and expand a little and drop that in. Of course, everybody's going, no, right? Because if I do an F5, then I've got 3 errors. And let's go ahead and fix a couple of them. Those aren't connected, so let's connect. and then do an F5. Everything works fine. Now I do an NCC. It says exports to implied. Alright. And the bodies are connected, but let me make another mistake here. Let me change, let's do a control I here, and let's make this a 10 by 2. And if I go take a look at my layout, somewhere on here, I see that those aren't the right sizes. Let's do an LVS. Oops. Let me go back over here to my NCC. Tools, NCC, halt after finding first mismatched cell. Okay. So what I should be able to do is go in here and hit F5. Oh, if you have an icon, I'll just tell you where I was going here. So if you have an icon and you do this, as soon as it hits this first error, it stops. It doesn't report the size errors. And so I think, oh, well, that's okay because I've got that first error. You may have 20 other errors in your cell. So what you want to do is you want to go back here to that NCC and you want to deselect this halt after finding first mismatched cell. If you don't do that, there could be, like I said, 20 errors in that cell and you won't know. You'll just think, oh, it works great, and it's just reporting the VCC and the ground issue. Okay, any questions? Alright, so let's save this, go back over here,